Javier asked me to talk about climate change in the context of, of sustainability. I assume, let's see, which way is this? I assume most of you are familiar with sustainability as the UN has defined it, Sustainability Development Goals. One of those down here, number 13, is called climate action. It's one of the 17 goals. And so what I'd like to do today is to focus on that topic. It's one that I suspect a number of you have probably studied and learned about, but also imagine some of you may not have gone too deeply into this. So I wanted to start with kind of a basic overview of climate change, what it is, what causes it, and why we care, what the impacts are. Then talk a bit about measures needed to deal with climate change. Key focus on policy drivers and the notion of innovation, which is, I think, at the heart of a lot of the work you're doing, and then talk a little bit about where things are headed. So first, just a primer, a basic review of what climate change is and how it works. Temperature is one of the key measures of climate. We'll talk a little bit about that later. And in the context of the planet, what is it that determines the temperature of the Earth? Fundamentally, it's an energy balance between solar energy coming in and terrestrial energy coming out. So basic physics says that any time an object has a temperature above absolute zero, it begins to radiate. So dynamically, as the sun starts to heat the Earth starts to warm, and it radiates back to space. Okay? And when the incoming and outgoing are in equilibrium, which is what nature will always seek, that determines the temperature. So it's actually a very simple calculation to figure out what the temperature of the Earth would be if it were just a rock, no atmosphere, nothing else around it. We can measure how much energy is coming in from the sun per square meter of surface, and we can calculate a temperature, and that turns out to be about minus 19 degrees Celsius. About 2 degrees below 0 Fahrenheit would be the temperature of the Earth if there were no atmosphere. So we wouldn't be here having this conversation. The real Earth has a very thin layer of atmosphere. This is not to scale. To scale, the atmosphere would be thinner than this little black line. It's really kind of like a little skin around the planet. It's really very, very thin. But in the atmosphere, besides nitrogen and oxygen, which is what air is mostly composed of, are a bunch of what are called trace gases, small amounts of a number of other gases and water vapor, which play a rather critical role in this overall energy balance. The characteristic of these gases is that they tend to absorb the energy that the Earth would normally radiate to space. It's kind of like putting a blanket around the planet. So what happens when that occurs? That destroys the balance between incoming and outgoing. So there's more coming in than going out, and that basically forces it. The term forcing is a technical term, actually. It forces the Earth to raise its temperature so that the outgoing again matches the incoming solar. So how much of an increase does that involve? In this case, with the atmosphere, the equilibrium temperature would come to about 15 degrees Celsius, around 60 degrees Fahrenheit, which is an increase of 34 degrees Celsius, a little over 60 degrees. So the greenhouse, what's called the greenhouse effect, has actually warmed the planet by over 30 degrees Celsius, around 60 degrees Fahrenheit. So small amounts of these gases have had a dramatic effect on the planet. Again, the major greenhouse gases we'll talk about: carbon dioxide, methane and nitrous oxides. Carbon dioxide arises naturally from anytime there's fires or combustion of carbon-bearing materials, including biomass, wood, and more recently fossil fuels like oil, coal, and natural gas. Methane also arises through various natural sources and nitrogen oxides, nitrous oxides as well. So these gases are formed and emitted to the atmosphere from both natural processes and also now increasingly from human activities. And it's those human activities that are really the focus of what we'll be talking about. Over the past roughly 150 years, this is the amount of these different gases that has been generated by human activities, mainly burning fuels for energy, burning coal, burning wood, burning natural gas, burning oil, which is putting more of these gases exponentially into the atmosphere. And as a result, the atmosphere has been changing demonstrably over the last 150 years, again in an exponential way. All of these concentrations have been going up. And the key reason is that these greenhouse gases are different from other air pollutants that we talk about. We've always worried about air pollution, health effects from things like fine particles and sulfur dioxide. Those traditional air pollutants, though, tend not to stay in the atmosphere very long. They react chemically, they dissolve in rainwater. If we stopped emitting those, they would basically come out of the atmosphere in days, weeks, or months. The key characteristic of greenhouse gases is that they don't react, they don't come out of the atmosphere very easily. In fact, they stay in the atmosphere and accumulate over decades, centuries, and even millennia. So even in this room, there are probably some CO2 molecules that were formed perhaps even 1,000 years ago. That's the key characteristic. So you can't just turn it off and expect it to go away. It's kind of like a bathtub with a small drain and a big faucet. We're filling the atmosphere faster than we're draining it, and that's causing the concentrations of these gases to increase in the atmosphere. There's one other gas I didn't mention that's also a very powerful greenhouse gas, and that's water, water vapor, H2O. We're putting a lot of that in the atmosphere as well. The key characteristic is that one doesn't accumulate. When the air gets saturated, it rains, it snows, it precipitates. So water vapor is a very powerful greenhouse gas, but it doesn't accumulate. And so it's typically not even often mentioned. So what's been happening in modern times? Have some of you seen this kind of graph before? This is the concentration of carbon dioxide measured in the atmosphere in Hawaii, in a remote area in the Pacific. A guy named Keeling from Scripps in California set this up back in the late 1950s, and this has been kind of the gold standard of what atmospheric concentrations have been doing. There's this kind of characteristic sawtooth. What's that about? What causes that? You know, why does it go up and down like that? Any idea? It's basically vegetation. So what happens in the summer now? Trees are growing, right? Leaves are growing. They're sucking CO2 out of the atmosphere and magically converting it into growth. So when that happens, the concentrations in the atmosphere measurably drop during the summer months. What happens in winter in the northern hemisphere, the leaves fall, they decay, they put the CO2 back into the atmosphere on an annual cycle. So you can actually measure that noticeably. It's a couple of parts per million. The key is that relative to where we've been for the past several thousand years, which is a level of a little less than 300 parts per million, 280 parts per million, we are now actually above 400 parts per million. So what does that mean? What kind of context? We're on a pathway where that 400 could potentially double by the end of the century. It kind of depends on how much more CO2 we put into the atmosphere. But to give it context, this is the picture that always keeps me up at night sometimes. This is about roughly almost 1 million years of history. So these are reconstructions of past levels of CO2 from ice cores. You go up to the Antarctica, you dig down, you're basically going back into history. You measure the CO2 in trapped air bubbles. So that's 800,000 years ago, a little less than 1 million years ago. Here we are today. So you see there's this kind of characteristic cycle of a couple of 100,000 years that has to do with long cycles of how the Earth rotates around the sun. But look, over the last 1 million years, here's 400 parts per million. Here's where we are today. Over the past 1 million years, we've never been that high. It's always been down around 300 million years. Where are we headed? That depends on how much more CO2 goes into the atmosphere over your lifetimes and your professional lifetimes. But right now, the pathway that we're headed on, let's see, is this working? Oh, here we go. Okay. That's the pathway we're on. If CO2 were to double by the end of the century, which is not inconceivable, we would be in a situation where nothing like this has happened in literally millions of years, both for the magnitude of the level and also the rate of change, how quickly things would happen. So what? I would always ask you to ask the so what question. Okay? So what? The so what is that as CO2 is changing, the blanket of the Earth is getting thicker, and so the Earth has to respond by increasing its temperature because it's trying to seek a new equilibrium. Here's some data as to what has actually happened and measured over the last roughly 150 years. There's no doubt that the Earth today is roughly 1 degree Celsius warmer than it was about 100 years ago, roughly 2 degrees Fahrenheit warmer, the average temperature. This is history. Some of these temperatures, which way do we have to point here? Over there. Whoops. So you go back. As a lot of you know, recent years have been some of the hottest on record. I'll show you some other numbers. The other important thing to kind of keep in mind is that, as in lots of other things, when you talk about averages, that kind of disguises a lot of important details. One of those is that some parts of the planet warm faster than others. Typically, the polar regions, you see, warm faster. These are pictures, these again are actual historical records of the difference in temperature in different regions relative to the average. So basically, the blue areas mean, in general, regions that are colder than the average, and the red areas are regions that are warmer than the average. So look, over 150 years ago, the northern regions, even parts of Europe, dark blue, were generally colder, as you'd expect. But gradually, here's 50 years ago, they were still colder, but not nearly as much. And today, those regions are actually warmer. The Arctic today is about 3 or 4 degrees warmer than the average temperature. So averages don't tell the whole story at all. These distributions matter a lot. This is where the ice is. That's ice that's starting to melt more rapidly than one would have